Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to discuss our week 5 hour 1 tutorial, which will cover for a new topic called electrochemistry, specifically 3.1 Voltaic Cell. So the learning objectives for non-face-to-face questions are to construct standard reductions or electrode potential series by using SHE and to predict spontaneity of redox reactions. Before discussing the questions, let's recall the content that you need to know for this hour based on the learning objectives. There are two terms that you need to be familiar with. One is electrode potential and one is cell potential. Electrode potentials involve only one half cell because the meaning of electrode potentials is potential developed between an electrode and an electrolyte. So, to find this electrode potential, we need to pair this with standard hydrogen electrode. As we know already, standard hydrogen electrode has a reference value of 0.00 volt. Next is cell potential. Cell potential is like this, where it is the potential developed by combining two half cells. So basically, you're going to have two active electrodes, and then we're going to look at the potential developed between them at the reading of voltmeter. So we're going to use the setup of Voltaic Cell. Based on the diagram given on the left, here are the summary for Voltaic Cell. So by definitions, this cell will generate electricity via spontaneous redox reactions. Spontaneous reactions takes place in this cell means movement of electron will initiated solely by the chemical reactions takes place in each half cell. So no other external force is applied like battery and so on. So means the operations of cell gonna be from chemical reactions to electrical energy. So electrons will move from anode to cathode. So how do we determine who's going to be the anode and who's going to be the cathode? So since we already know that reactions takes place here is spontaneous redox reactions, then we need to have anode with more electron on it and cathode with less electron on it. So how do we know this? By looking at the electrode given in the diagram. So we have zinc on the left and copper on the right. If we look at the SRP table, we know that zinc gonna have more negative value compared to copper with more positive value. So the negative value will indicate that they have more electrons, means electron will move from the left to the right. Okay, so this terminal gonna be negative while the other terminal gonna be positive because they're gonna accept electron. So the one that releases electron will undergo oxidation reactions, while the one that accepts electron gonna undergo reductions process. So from this voltaic cell, we can calculate the value that have on here, which is the voltmeter. So we're gonna use this formula of standard cell potential. Please look at this symbol, the superscript 0 means that they are conducted at standard conditions, which is 25 degrees Celsius, 1 atm and also 1 molar. So we can simply calculate the E naught cell equal to E naught cathode minus E naught anode. And from the value, whether they're going to have positive or negative or 0, so we're going to indicate them in terms of spontaneity of a reactions. If we have E naught cell greater than 0, means we're going to have spontaneous reactions. The electrode can initiate the reactions on its own. If we have E naught cell equal to 0, means the reactions is in equilibrium. And lastly, if the E naught cell is less than 0, means we're going to have non-spontaneous reactions. As the first questions for non-face-to-face, the question tells you the magnitude of the standard reduction potentials of two metals X and Y are as follows. So given to you the chemical equations in terms of reductions process, because this value comes from the standard reduction potential table. But please note here that the E naught with modulus sign denotes only the magnitude without the sign of the E naught value shown, means that we don't even know yet which of those will have more positive or more negative value, because we need to indicate the value and also the sign to determine who's going to be the anode and who's going to be the cathode. So when the half cell of X and Y are connected, electrons flows from X to Y. So we are given one hint regarding the movement of electron x to y. And then when x is connected to SHE, where we can find our electrode potential, the electrons also flow from x and SHE. The question asks you to determine whether the E-note values of the half cell reactions are positive or negative. So from the questions, we know that the electron will move from X to SHE and X to Y. So we can conclude that X is going to release electron. So process that involve the removal of electron is known as oxidations. Therefore, electrode must have a more negative value to release electron. And as for Y, we can take it to undergo reductions, so they're going to accept electrons. Y will undergo reductions, therefore electrode must have positive E-note value to accept electron. So we simply add negative sign on X E-note value and positive sign on Y E-note value. Question B asks you to calculate the standard EMF of a cell consisting of X and Y electrodes. So EMF is another name used to say cell potential. So please note that we have standard at the front of EMF, means they are the same as E-note cell. So the calculations that involve E-note cell is known by using this formula. E-note cell equal to E-note cathode minus E-note anode. So we have already determined who's going to undergo oxidations and reductions. So cathode will be the one that accepts electron, means they're going to have more positive value, which in this case Y. While anode is the one that releases electron, means they're going to have more negative value, means we have anode of X. So we simply substitute the value of the E-note by having both sign, okay? And lastly, you will get potential difference between X and Y is positive 0.59 volt. Please write the positive or negative whenever necessary, because if you don't put this value, we're going to be confused with the spontaneity of reactions. Question 2 wants you to predict whether the following reactions will occur spontaneously in aqueous solutions at 25 degrees Celsius. Assume that the initial concentrations of the dissolved species are all 1 molar. So the keyword given here is spontaneous, and also standard conditions of 25 degrees Celsius and 1 molar. So basically the questions wants you to determine whether this reaction is spontaneous or not. So we know already we are going to determine the spontaneity of reactions. Then we need to use the formula of E-note cell equal to E-note cathode minus E-note anode. So we have 3 conditions altogether. If they are greater than 0, means they're going to have spontaneous reactions. If the value is equal to 0, means they're going to have equilibrium reactions. And lastly, if the value of E-note cell is less than 0, means they're going to have non-spontaneous reactions. So given to you 4 balanced reactions that involve the oxidations and also reductions in a chemical cell. So we're going to use green colored pen to indicate oxidations process take place, and also blue colored pen to indicate reductions process. So we'll start with 2A, where we have calcium to become calcium 2+. So basically, which reactions will take place here? Oxidations or reductions? So they're going to release electron, means they're going to have oxidations reactions. Oxidations will take place at anode. Okay, and then for Cd2+, automatically they're going to undergo reductions. So from the formula, we know that E-note cathode must minus E-note anode. So how do we know this value? We'll look at the SRP table, where we have all the values there, even though the table gives you in terms of reductions process. But if you stick to the formula of cathode minus anode, then you can simply take the value and simply substitute. You don't need to change anything. So just use the E-note cell equal to E-note cathode minus E-note anode. Okay, so we're gonna substitute the value where Cd2+ to become Cd have the value of negative 0.40, and then we're going to minus it with E naught N naught, which in this case calcium with negative 2.87. Lastly, your E naught cell will become positive 2.47 volt. Since we have value of E naught cell greater than 0, means we're going to have spontaneous reactions. Next, for 2B, we have 2Br minus to become Br2 and also Sn2 plus to become Sn. So 2Br minus to become Br2 will be the oxidations, will be the anode, and Sn2 plus will undergo reductions to become Sn. So the cathode is Sn2 plus. So see, we are going to substitute the value where Sn2 plus to become Sn will have the value of negative 0.14. So minus the anode, we have 2Br minus to become 2Br. So we're going to have value of negative 1.21 volt. So negative value indicates the E naught cell has value less than 0. Therefore, non-spontaneous reactions takes place. For 2C, we have silver react with nickels to form 2Ag plus and nickel solid. So from these reactions, we know that the silver will undergo oxidations while nickel will undergo reduction. So nickel will be the cathode with value of negative 0.25 and silver with value of positive 0.80. Once we calculate this value, we're going to get negative 1.05 volt. Negative means less than 0, therefore non-spontaneous reactions. So for D, we have Cu plus react with Fe3 plus aqueous to form Cu2 plus and Fe2 plus. So from these reactions, we know that the Cu plus will undergo oxidations to become Cu2 plus and Fe3 plus will undergo reductions to form Fe2 plus. So once we substitute the value of Fe of 0.77 and Cu with value of positive 0.15, we're going to get E naught cell equal to positive 0.62 volt. Positive value indicates E naught cell with value greater than 0, means spontaneous reactions will take place. Question 3 asks you to choose which species in each pair is a better reducing agent under standard state conditions. So what is meant by reducing agent? Reducing agent is basically a species that undergo oxidations. We've already talked about this previously. We know that when the species undergo oxidations, means they're gonna have more electrons on it. Therefore, their E naught value should have more negative value. So we're gonna compare between the two species given who's got more negative value based on the SRP table. So make sure that you have your SRP table with you, and then let's compare the two values. So for Na, which is the sodium, we're going to have a value of negative 2.71 volt, while lithium with E naught value of negative 3.05 volts. So between these two, who's got greater value in terms of E naught? So lithium. So we're going to have lithium as a species which act as a better reducing agent. Next, we have H2 and also I minus. So H2, we know that this is hydrogen, means they're going to have only 0.00 volt. Compared to the I minus, they have positive 0.53 volt. So between 0 and 0.53, who's got more negative value? Hydrogen. So hydrogen gonna be a better reducing agent compared to I minus. Between Fe2 plus and silver, so Fe2 plus, we have a value of positive 0.77 volt, compared with silver with E-node cell of the E-node electrode of positive 0.80 volt. So 0.77 and 0.80. More negative value is Fe2 plus because 0.77 is less than 0.80. They are not necessary to have negative sign on it. As long as they got lower value than the other one, they are considered to be more negative. And lastly, we have Br minus versus cobalt 2 plus. So we have Br with negative 1.07 volt versus negative 0.28 volts. So which of those will have more negative value? So Br minus got more negative value, therefore they're going to be a better reducing agent than cobalt. For face-to-face questions, you should be able to compare the relative strength of oxidizing or reducing agents and to calculate the standard cell potential. Shown on the slide, the standard reduction potential table. From the name itself, we could see only reductions reactions are listed on this table, each with specific values. So how do we determine these specific values? Recall again the two terms we've learned at the very beginning of this tutorial, where we have electrode potential and also cell potential. So these values are basically electrode potential. So how do we know this? By pairing it up with hydrogen electrode with electrode potential of 0.00 volt. So the species that undergo reductions is known as oxidizing agent, while species that undergo oxidations is known as reducing agent. So we could see the strength of oxidizing agent increases from lithium down here to fluorine up here. While for strength of reducing agent, the increases from up here to down the list of lithium. For the first questions in face-to-face tutorials, we are given standard electrode potentials for silver and lead, which are 0.799 volt and negative 0.126 volt respectively. So you need to determine the anode and the cathode from these reactions. So we've learned already that the one that have more negative value will undergo oxidations, therefore this will become the anode. Okay. And then for the value that have more positive value, gonna undergo reductions, therefore will become the cathode. So the anode will be the lead electrode, while the cathode will be the silver electrode. Next, we have to calculate the standard cell potential. So standard cell potential is basically E-node cell. So we have the formula of E-node cell equal to E-node cathode minus E-node anode. Since we've already determined that silver will become the cathode and lead will become the anode, means we're gonna have positive 0.799 volt minus, and you must put the bracket together with the negative 0.126 volt. And lastly, your cell potential gonna be positive 0.925 volts. So if they got more positive value, means they're gonna have spontaneous reactions. For B, the reactions given is 2Ce4 plus in aqueous react with CO in solid to give 2Ce3 plus and CO2 plus in aqueous with E-node of positive 1.89 volt. So the E-node given here is basically the E-node cell, not the E-node of electrode. So this is one information have been given to you, the E-node cell. And then for the questions, they continue with the standard reduction potential for CO. So means this is for only CO. The individual half cell is negative 0.28 volts. So you have information regarding the E-node cell and also the electrode potential of cobalt. So now you need to calculate the standard reduction potential for the change from Ce4 plus to Ce3 plus. So you need to find the electrode potential of Ce. So from the balance equations given, we could see that cobalt will undergo oxidations, means they're going to release electron, while the Ce4 plus gonna undergo reductions because they're gonna accept electron. So we're gonna use exactly the same formula just like before. E naught cell minus E naught cathode minus E naught anode. And then our Ce gonna be the one that undergo reductions, means they're gonna be the cathode. So substitute the value. We want to find the E naught cathode. Lastly, you're gonna get standard reduction potential of Ce is positive 1.61 volt. For questions 2, you are given cell notations. So cell notations are written from anode to cathode. So on the left hand side, we start with anode where oxidation takes place, and cathode to the right hand side. So they undergo reductions. And then given to you here, the E naught cell of the reactions, where you know that E naught cell is equal to E naught cathode minus E naught anode. So the question asks you to balance the equations for the spontaneous reactions. What is meant by balance equations? Balance equations can only be determined when all the electron has been transferred from one half cell to another. So means that you need to translate the cell notations given into oxidations and reductions reaction respectively. So we're gonna have anode which undergo oxidations consists of silver, so we're gonna write it as this half cell, and then followed by the unknown M electrode which undergo reductions. So in order for you to get the balance equation, we need to first cancel out the electron. But since we've got number of electrons that is not equal to one another, we cannot simply cancel them out. So in order to cancel them out, we need to first make the number of electrons equal. So by multiplying the silver species with 3, then we're going to cancel this electron out, leaving only the species involved without electrons. So we're going to have overall equations of 3Ag react with M3 plus to become 3Ag plus and M solid. So this is your overall equations. Next, they ask you to determine the oxidizing agent. So we know that oxidizing agent is the species that undergo reductions. So look at your reductions reactions. You have M3 plus react with 3 electrons. The species that undergo reductions is M3 plus. For question C, they ask you to calculate the electrode potential of M. So given to you the electrode potential of Ag, which is 0.80, and also the E naught cell. So you can simply substitute into this formula, and then you can find the final value of positive 1.80 volt. As for the last question for this hour, you need to predict whether Fe3 plus can oxidize I minus to become I2 under standard state conditions. So what is meant by this statement really? So this statement wants to tell you if this species can really oxidize the other species, means the reactions can occur spontaneously. So how do we know that the reaction can occur spontaneously? By looking at the E naught cell value. So we've already learned about the spontaneity of reactions. We have 3 conditions altogether. If you've got E naught cell greater than 0, means the reactions will occur spontaneously. Alright, so let's check. We have these 2 values comes from I2 and also the Fe3 plus with positive 0.53 volts and also positive 0.77 volt. You need to first indicate who's going to be the anode and cathode. So anode undergo oxidations, means they're going to have more negative value. So between these two, the 0.53 will become the anode, while the 0.77 will become the cathode. So you're going to substitute this value into the E naught cell equal to E naught cathode minus E naught anode, and substitute, then you will get E naught cell of positive 0.24 volt means that positive value here indicates that this Fe3 plus can oxidize I minus to I2. Thank you for your attention. See you in the next hour. Bye.